Hello guys, how are you doing? Today is the first session of tutorial for chapter 3. I'm gonna illustrate you question 3.10 from section 3.2 of chapter 3, which is titled as F equal to MA along a streamline. So the question is, an incompressible fluid flows steady past a circular cylinder as shown in figure P 3.10 as this. Let me just write down the assumptions. Incompressible, steady, inviscid. It actually forgot to tell you about that. Inviscid. This means we can use Bernoulli equation or something like that. The first form of that. I'm going to write it down. The rest is the fluid velocity along the dividing streamline from minus infinity to minus a is like this. Minus infinity x minus a. The velocity is functioned as v0 multiplied by 1 minus a to power 3 divided by x to power 3, where a is the radius of the cylinder, and v0 is the upstream velocity, like this. For part A, it wants us to determine the pressure gradient along a streamline. So, if we do write the Bernoulli equation for the part A, we're going to have it as this. Let me just go through my written text. Yeah, it's like minus gamma sine theta minus round p to round x is equal to minus rho v round v to round x. Round v to round x. Let me just clean up here to write it down over here. As we are moving along the horizontal line, this means that sine theta is going to be 0, as the theta is equal to 0. So we have it as this. And moreover, we are trying to have our coordinates as well. Here we have s, minus rho to rho over s is equal to rho to rho x. If we just substitute it here, we're going to have it as this. As this. If we just substitute the v function in this, we're going to have the pressure gradient as round p to round x is equal to Let me just write the whole equation. Don't disturb you with the rest. If we just take the deviation according to x and write it over here, we're going to have the pressure gradient as rho p, round p to round x is equal to minus 2 rho a to power 2, yeah, a to power 2. Let me just have it cleaned. V0 to power 2 multiplied by 1 minus a over x to power 2, yeah, totally divided by x to power 3. So, taking the integration from this equation, we're going to have it as this. Integration of dp, because we're just analyzing everything in the one dimension, so we can just transfer round p to dp. From p0 to p is equal to p minus p0 as minus 2a to power 2 v0 to power 2 integration from minus infinity to minus a of 1 minus a over x to power 3 dx over, excuse me, this is 2. This is 2, x to power 3. Doing the whole integration, we're going to have it as this. P is equal to P0 plus rho V0 to power 2 multiplied by A over X to power 2 minus 1 over 2, excuse me, it's infinity over here, yeah, multiplied by a over x to whole power 4, yeah. We're going to have it as this. This is for the part A. It's just doing the integration and the mathematical calculation. It's not a really big deal. From minus infinity to minus a. For the part B, we are, we have just done the whole thing for part A and B. Excuse me, I just messed it up. It's just for part A and part B. Part A was to identify the pressure gradient, which was this, yeah. And for part B, the question wanted us to find out if the upstream pressure is P0. If the upstream pressure is P0, integrate the pressure gradient to obtain the pressure and the function of pressure as x. This is the P as function of x. We have just all done the whole part of A and B together. For the part C, let me just erase everything to have the place to write the part C down. So, part C. Yeah. The part C wants us to show from the result of part B that the pressure at the stagnation point, which is x as minus a, is P0 plus rho V0 to power 2 divided by 1/2. So, from part B, we had the pressure as function of x as P0 V0 to power 2 multiplied by A over x to power 2 minus 1/2 A over x to power 4. If we just replace x as minus a, we're going to have it as this, minus 1 as this. So the total combination of this is going to be 1/2. So excuse me, there's a P0 over here. P0 plus rho. We're going to have it as this. Px is equal to Px as minus a is equal to P0 plus 1 over rho V0 to power 2. Rho V0 to power 2. There's another way to obtain this. If we just write the Bernoulli equation from point 1 to point 2, which at point 1 we have V1 as V0, P1 as P0, and Z1 as Z0. And for the point 2, we have it as this. X2 is equal to minus A, Z1 is equal to Z2, and the pressure is going to be resolved. P1 plus 1 over 2 rho V1 to power 2 plus gamma Z1, excuse me, gamma Z1 is equal to P2 plus 1 over 2 rho V2 to power 2 plus gamma Z2. If we just replace all of these to this equation, which is Bernoulli equation, we're gonna drive it as this. So this was the whole solution for question 3.10 from section 2.2 of chapter 3, which was F equal to MA along a streamline. I hope you have grasped the whole thing, and I'm really appreciated that you have accompanied me through this moment of this video. First of all, try to keep yourself at the calm situation, and most important thing is that subscribe the channel in order to get the notification of upcoming tutorial sessions. See you in the next sessions.